A crucial clue in the search for extraterrestrial life is just around the corner, in cosmic terms. Discovered in 2016, the planet called Proxima b circles our Sun's nearest neighboring star, Proxima Centauri. Revealed by the telltale wobbles its gravitational tug elicits upon its star, this world is slightly more massive than Earth, and, like the Earth, resides in Proxima Centauri's habitable zone, a circumstellar region in which warmth from starlight could conceivably allow liquid water to exist upon a rocky planet's surface. Beyond that, not much more is known about this planet, and its similarities to our own earthly situation may end there. Proxima Centauri is a red dwarf, a ruddy stellar runt shining with only about 1/1000th the brilliance of our far larger yellow star. Its planet's orbit is correspondingly scaled down, with a year that is only 11 days, not 365, placing it nearly 10 times closer in than Mercury is to the Sunday. And while starlight may be sufficient to sustain liquid water there, other effects of that close proximity, a far more luminous phase of the shrunken star's youth, steady bombardment by powerful stellar winds and X-ray flares could have long ago swept away the planet's air, moisture, and any possibility for surface life. Around red dwarfs, it seems, habitable zones and danger zones are much the same thing, and ever since Proxima b's discovery scientists have been arguing about its prospects for life. The latest salvo in the debate emerged on July 24, in a paper from a group of researchers whose modeling suggested that, even protected by a potent magnetic field, an Earth-like atmosphere on Proxima b would still rapidly dissipate due to intense stellar radiation. Of course, no one is really convinced the case is closed. There are so many caveats, it's really too early to answer the question of Proxima b's habitability, says the planet's foremost discoverer, Guillaume Anglada-Escude, an astronomer at Queen Mary University of London. It's just a matter of philosophy and simulations right now. What we need is actual data. All this matters a great deal to astrobiologists, not just because Proxima b could be an Earth next door, but also because worlds such as this probably constitute the bulk of potentially habitable planetary real estate in the universe. Red dwarfs are the longest-lived and most abundant variety of star, far outnumbering larger, brighter stars in the Milky Way and other large galaxies, and statistics suggest the bulk of them should harbor small planets like Proxima b in not too hot, not too cold orbits. Ideally, astronomers would like to investigate some of these promising planets around the nearest red dwarfs, looking for signs of atmospheric gases such as water vapor, carbon dioxide, oxygen, and methane that on Earth at least hint at the presence of habitable conditions and even of life itself. Such measurements are easiest for relatively nearby planets that transit across the faces of their stars as seen from Earth, when any appreciable atmosphere will manifest as a ring of refracted starlight limning a world's shadow in our telescopes. Proxima b, alas, does not appear to transit, and studies of transiting potentially habitable planets around more distant red dwarfs have yet to conclusively reveal any details of their atmospheres or even whether they have atmospheres at all. This is a really big question for life, writ large across the galaxy, says Victoria Meadows, Director of Astrobiology at the University of Washington. These are the most common types of habitable zone planets in the universe, and it's totally up in the air at the moment as to whether or not they can keep their atmospheres. If it turns out that all of them have had their atmospheres completely stripped away, then the probability of life elsewhere takes a significant hit. Remotely sniffing the air of these tantalizing worlds is no easy task, and is unlikely to occur sooner than the end of this decade, if not well into the next. The first observations could be made by NASA's Infrared James Webb Space Telescope, launching in 2018, followed in the mid-2020s by a new generation of ground-based extremely large telescopes with 30-meter mirrors. However, the payoff could be immense. In a forthcoming paper submitted to the Astrophysical Journal, the Harvard-Smithsonian Center for Astrophysics astronomer Caroline Morley and colleagues conclude that with a total investment of as little as a week of observing time, Webb could conceivably deliver statistically significant detections of Earth-like atmospheric conditions upon a handful of small planets transiting nearby red dwarf stars. Or, of course, Webb could find instead that those worlds are airless rocks. Whether such investments will happen at all is far from certain. With a nominal lifetime of only 5 years and astronomers worldwide clamoring to use it, the telescope is destined to become the most oversubscribed and in-demand scientific instrument humans have ever built. In the meantime, some researchers are focusing on ways to use Webb to simply detect an atmosphere or rule one out upon the closest potentially life-friendly red dwarf world. Find that Proxima b has managed to keep an appreciable atmosphere in spite of the barrage of physical insults from its stellar host, and you have taken a big step toward showing the universe is filled with biologically promising red dwarf worlds. Finding it has no atmosphere could, by contrast, bolster the case that red dwarfs are by and large dead ends in the search for alien life. It may sound arrogant, but using Webb to prove that Proxima b has an atmosphere would be one of the biggest scientific achievements it could make, says Ignace Snellen, an astronomer at the University of Leiden. If Webb does that, I think the project would have to be considered a success, no matter what else it does. Webb was never meant to study small, dim planets around other suns. Instead, its instruments and gargantuan 6.5-meter mirror, the largest yet flown in space, were designed to study the faint infrared light from the universe's first stars and galaxies. Even so, astronomers have devised at least two methods for the telescope to peer at Proxima b. Both rely on the telescope's mid-infrared instrument, called MIRI, a cryogenically cooled, coffee table-size imager and spectrograph that, once in space, will operate at temperatures just 7 degrees above absolute zero. Although Proxima b does not transit and is too close to its star for Webb to directly see, MIRI's ultra-cold detectors should be able to tease out hints of the world's emitted heat intermingled with the star's light, a situation akin to looking for the glow of a light bulb backlit by the sunday. This potential use for MIRI was first mentioned by Proxima b's discoverers and collaborators in a paper shortly after the announcement of the planet's existence, and elaborated on in a later study by Laura Kreidberg and Avi Loeb, both at the Harvard-Smithsonian Center for Astrophysics. The technique calls for using MIRI to monitor the system for the entirety of at least one full 11-day orbit of Proxima b, looking for temperature differences between its cold, dark night side and warm, illuminated day side as it revolves around its star. Minimal thermal changes between the day and night sides would betray the presence of an atmosphere that is redistributing heat, whereas large contrasts would suggest the planet has no atmosphere at all. Extended to a 60-day-long stare with MIRI, the same technique might even reveal the presence, or absence, of atmospheric ozone, a potential biosignature gas that could be indicative of photosynthetic organisms or other living things. Such observations would not be easy, Kreidberg says. 11 uninterrupted days of observing time, not to mention 60, would be a big ask for Webb as astronomers worldwide compete to use the precious resource. What's more, Proxima Centauri is a flare star, continually erupting in bursts of light that, unless painstakingly filtered out in some as yet undefined manner, could outshine the far fainter thermal signals from Proxima b. The second method for detecting a Proxima b atmosphere emerged in a study posted online July 26 and led by Snellen, the University of Leiden astronomer. Rather than search for the atmosphere via diurnal temperature changes, Snellen proposes using MIRI to look for just one possible constituent of the planet's air, carbon dioxide. Thanks to its well-known ability to absorb heat, that is, infrared light, the greenhouse gas imprints a barcode-like series of shadowy absorption lines upon any starlight passing through it. MIRI's spectrograph cannot readily discern carbon dioxide's absorption lines against the overwhelmingly brighter background of starlight, but Snellen argues that careful calibration with model-based templates will allow a blurry glimpse of carbon dioxide's barcode to surface from the sea of stellar glare, in which aggregates of individual lines would appear as broad peaks and valleys in MIRI's measurements. This approach, Snellen says, would require a few days of observation, slightly less time than measuring Proxima b's full phase curve across an entire orbit, and would not be susceptible to the contaminating effects of stellar flares. It would also, however, require an intimate understanding of MIRI's performance in space and Proxima Centauri's infrared emissions that researchers presently lack. The challenge is to show that this method works, Snellen says, but you can basically only show that by actually doing it. Both his and Kreidberg's techniques would likely require several stepping stone observations, in which MIRI would target a series of larger, hotter planets that are progressively more difficult to study. Those preliminary tests, plus other technical challenges associated with these ambitious observations, would probably preclude Webb scrutinizing Proxima b until at least a year into its primary mission. If his method does prove to work for Proxima b, Snellen says, it gives you an independent detection of the planet, as well as a clear indication it has an atmosphere, and not only that, but also that the atmosphere contains carbon dioxide. Carbon dioxide is a very important gas, a greenhouse gas that can tell you a lot about a planet's atmosphere and climate. If we found it at Proxima b, it would tell us that this planet is maybe a bit more like the terrestrial worlds we see in our own solar system. Signs of carbon dioxide in Proxima b's air would essentially confirm the planet is rocky and not a bloated, hydrogen-rich ball of gas, Meadows says, but otherwise could point to several mutually independent environments. It could mean the planet is a runaway greenhouse world like Venus, where earlier, more luminous stages of Proxima Centauri's stellar evolution boiled the ocean and baked carbon dioxide out of rocks. It could also mean the planet is a warmed-up version of Saturn's largest moon, Titan, a strange, slushy mud ball mostly made of water and hydrocarbons simmering away beneath a smoggy, hazy atmosphere. Or it could mean Proxima b is a cool, arid rocky world with a thin atmosphere like Mars, or, just maybe, an even more wet, warm, and welcoming place much like Earth. Conversely, finding no carbon dioxide wouldn't necessarily mean Proxima b has no atmosphere, or even that it lacks the greenhouse gas, a hydrogen-rich atmosphere, or thick, high-altitude clouds, for instance, could also explain a null detection. Kreidberg sees both sets of observations searching for Proxima b's phase curve as well as its carbon dioxide as complementary ways to solve the mystery of whether or not the planet has an atmosphere. And while lavishing the planet with days or even weeks of Webb's limited time may seem excessive, the insights it could provide make it worthwhile. There is only one potentially habitable planet around the Sun's nearest star, and we only have a handful of nearby, Earth-size planets that are possible to study with Webb, she says. We have no idea what their atmospheres are like or if they can even hang on to an atmosphere all. So we should try every trick in the book to learn what we can about them. Every astronomer I know is holding her breath for what we find out.